already more or less completing our subject matter here. Be very, very thorough with your subject. It is not only to pass this ME or semester exams, it is also to be capable of doing well if your interviews and MMD examinations put these questions to you. So you need to have that thoroughly understood. And boys, I couldn't take the morning class because I had an appointment with a medical clinic. So that is why I am taking the class in the afternoon. It's fortunate that you don't have a class in the afternoon and I can actually complete part of the syllabus here. And I hope everybody is able to attend because this message should have gone to everybody. And Shubhankar must have put this across to everybody. 1401. We'll wait for. Yeah, I hope you have got that new order which director has issued, and it is regarding attendance in class. You're supposed to have proper shave, proper haircut. You're supposed to wear clothes in order. Okay, it's part of your. See, the university is trying to do the best it can to prepare boys on an all-round basis. It is not online classes that is contributing to your development. It is some level of character building, some level of personality building, some little attitude building. So all these parameters actually you get in the college. And right now we are online, so these things really cannot be put across. But even at the minimal state, whatever little we can put across to you is asking you to be well dressed for a class. Is something that has to come from within you. If you're not properly dressed, I can't see you, I cannot check on you, I cannot do anything about you. It is up to you, it is left to you. You want an improved personality, you want an improved character, a good attitude. So that is why that order says the boys who are coming on online classes, they must also be well dressed, haircut, this, that, all these things. They are not intended to force you with rules. They are intended to build your personality so that you automatically get into that frame of mind where there is an official interaction that you will be making yourself presentable. That is the attitude we are trying to build into the students. Given these difficult pandemic times, we cannot put you in front of us. We cannot have face-to-face interaction. The only interaction is through online. And no matter how far away you are still a concern of us. You are still a concern for the university. You are a product of the university. So what you graduate with is what has been imparted to you during your time over here. And it is not only book knowledge, it is not only academic information that has been put into you. What the institution tries to do is build your character, build your personality, and build your attitude. All these three are also prepared during your stay in the campus. And you do have your colleagues, your batchmates, your juniors, your seniors, all of them. So it is an ideal situation where you know how to deal with people, how to mix with people, because you have to work as a team on board the ship. So these are the reasons why we have the rules in place in our campus. It is quite unlike other colleges. Other colleges don't bother what you're wearing, how you come by, whether you're keeping a beard or keeping a shave, nothing. Tries to instill a sense of discipline, a sense of camaraderie. That means you're working as a team with your batchmates. So that is why we want you to have a lot of interaction with batchmates. This is the official or the program that has been developed in our institute, which has produced some of the finest marine engineers all over the world. So if you follow in the footsteps of what has been imparted to the students, you will definitely make some of the best engineers in the country. So do follow up on those orders that have been given by the director. If you haven't got that order, I will post it to you after class and send it as an email attachment for everybody to read. That is the whole purpose, the reason. You don't become good marine engineers by scoring big marks in the exams. No way. That is not the way you become a good quality engineer. You have to be developed in all spheres. In other words, you must be good to communicate with. You must be making yourself presentable. You must develop a personality where people will sit up to listen to you, because ultimately you're going to be an officer under training. Ultimately, you are an officer under training, and by the time you graduate, you will have that officer-like qualities. That is what is trying to be imparted to you during your 4 years period. There is one little piece which I will give you from my side. It is not there in any book. It is not there in any manual. It is not there in any instruction book or rules, regulation. If you want to be an officer, there is one basic theme that you must follow, and that is don't tell a lie. Don't tell a lie. If you don't want to tell a lie, at the best, you decline to answer. An officer does not tell a lie. Of course, in today's world, it's become a ridiculous statement, but that is the truth. That is a fact. An officer does not tell a lie. If the officer does not want to tell a lie and at the same time he does not want to tell the truth, he may decline to answer a question. He may say, I decline to answer that question. You draw your own conclusions. That's the best way to get off from a situation where you are compelled to tell a truth which is damaging to anything and anybody. So best is not to give the answer and decline to answer, with the other party being given the benefit of drawing its own conclusions. So if you can do that, you have got officer-like qualities. But 99% do not tell a lie. Face the music. Face the music. Whatever happens will happen. Let us see. That sort of an attitude, if you can develop, you will become a good quality officer. All right, we have 29 boys. So still a lot of them are yet to come in. But anyway, today I will allow them to come in even if they are late, because I myself have changed the whole program. So let's proceed with our subject where we left off, and we had left off as a fuel injector. I hope you are able to draw this diagram in an exam if at all it comes to explaining how a fuel injector works. In any diagram, please do use a scale and a pencil, or if you can, use a pen for drawing a diagram. I always encourage using a pencil for a diagram. But I will also tell you one matter which is of concern, because we are doing the correction of the answer scripts. Sometimes when you draw with a pencil and on the side you write with the ink, the scanning device will scan the ink written statements very clearly, and the pencil lines will become very faded. So if at all you use a pencil, make sure that pencil is dark or very soft pencil, and you make deep lines. So the images are very dark colored, in the sense they should not look faded when the office scans your answer script and puts it to us. There are instances where I've had difficulty trying to figure out whether the diagram is correct or not. And that is largely because the diagrams are coming very light. And they come light if you draw with a pencil and do not make dark lines on them. If you have a very hard pencil by mistake, use a pen to go over the lines you have drawn with the pencil. Otherwise, the diagrams don't come out clearly after they are scanned if they are made with a pencil. But the ink part of it comes very clearly. That's one of, I suppose, the drawback of a scanning item, because pencil lines don't come. Similarly, if you use red ink to draw and then you scan it, it doesn't come easily. Or you make a Xerox copy of that, the red part does not come. So avoid using red ink or any other ink, other colors other than black or blue. So even if you're drawing a diagram, you draw it with a pencil, you overline it with a pen, it'll come out very clearly. So this is your fuel injector, what you see. This is your pressure chamber inside, and the fuel which comes into the fuel injector pushes the injector up. Initially, the pressure is acting on this annular surface because the valve is seated on a thin ring over here. This thin ring seat is because you have a seat difference angle of 1 to 3 degrees. In other words, the angle of the seat on the nozzle is larger than the angle on the seat of the uh, sorry, it'll be other one. Angle of the seat of the cone is larger than the angle of the seat of the nozzle. So this is intended to have a seating of the valve on a thin line. So that actual seating is on a thin line and it ensures positive closing. If it was on two flat surfaces and for any reason there is some dirt between the surfaces, then the valve will not sit. And then leakage will start taking place. Once the oil starts leaking, then it will start dripping. And if it starts dripping, then the quality of combustion will be very badly hampered. Okay, so this is the hydraulic pressure acting on the annular area, lifts the needle valve. Thereafter, the valve lifts very rapidly because the whole pressure is under the valve. And then the valve lifts by an amount which is equal to the valve lift. The nozzle holes are very small. They are small as a needle hole. So this proportion, 4:1, where the length of the hole as compared to the diameter hole gives rise to very small quantities or very small particles of fuel emanating from the nozzle hole. One of the problems in this particular type of fuel injector has been this sac volume. This sac volume is a space wherein oil remains even after the valve closes. So what oil has been discharged, thereafter whatever oil is collected in this sac volume remains in place. And since this nozzle is exposed to the combustion chamber or the combustion spaces, it starts overheating. The moment this oil starts overheating, it starts oozing out. You understand what is oozing out? It is same as seeping out. So once it starts oozing out, the oil at the tip starts carbonizing because the heat in the combustion chamber is enormous. 300 degrees centigrade, 250 to 300 definitely. So that oil starts carbonizing. And once carbon starts accumulating here, it forms what is called trumpet. Trumpet. Trumpet formation is a characteristic overheating of the nozzle spaces. That means the oil over here starts overheating and therefore the carbonization of the fuel starts going. It is like a growth. It is like a growth, and the growth is in the shape of a trumpet. And actually you can break it off from the injector. When you lift out the injector from the cylinder head, you will see the growth on different holes, maybe 2, maybe 3, maybe 4 of them. And they are about 1.5 to 2 inches large for a big injector. And they can be broken off. And it's like koila, hard as coal. So that is what happens. And it happens because this particular nozzle area gets overheated. So the solution is to have a cooling water space in this nozzle itself in this region. I have not shown it, but in some injectors, they have this space over here with a space for cooling water. This cooling water comes similarly to what you see the fuel coming in through a different section of the nozzle. So that cooling water comes in, cools this particular sac volume area, and then goes out again. It is a problem of keeping this space, cooling water space, clean because the space is very small and there is a tendency of accumulation of sediment. This sediment, if it accumulates, it solidifies. And after it solidifies, it blocks the whole passage. Then in most fuel injectors I have seen, over a period of time, the cooling water hardly comes out. So what we do, we invert the cooling water, invert the fuel injector, and then pass the cooling water, and then see from the other side if the cooling water is coming or not. Sometimes it comes in a trickle, so that is not good enough. It has to come with a reasonable force to provide the adequate cooling. So that sometimes does not happen, and the problem is this part gets choked, and then you have this trumpet formation. The fuel which is in this sac volume must reach a viscosity at 12 to 15 centistokes. Modern nozzles have reduced sac volume to reduce NOx and reduce trumpet formation also. NOx is nitrogen oxide, which is a pollution. We will not go into that subject at the moment, but how is it reduced is in the next diagram. This is the modern slide type of fuel injector. This part you need not worry about. What you need to worry about is the point where the nozzle is. You see the nozzle here? This is covered by means of a piston. This piston is a hollow piston. Only circumferentially it has covered the spaces and it has been fitted into this slot over here. So moment the piston is in this position as you see it, it has blocked the nozzle hole completely. So there is no escape of any oil coming from here or seeping out from these spaces. So if at all this valve has to work, this entire spindle which is holding the piston will lift and allow the entire oil to pass through the piston and into this space over here and then be discharged with the required level of atomization and penetration. Okay, so this slide type of fuel injector is the more modern fuel injector that is used in most of these large engines. This has removed chances of what you call trumpet formation, and also it has stopped chances of any NOx formation. It has reduced NOx formation. You don't need to bother about drawing this part. All you need to bother about is just this nozzle, if at all you're asked. What is the improvement that has come about in the original fuel injector with a sac volume? You say the original injector is gradually being moved on and a slide type of fuel injector is being utilized with the objective of reducing the sac volume, in fact, eliminating the sac volume and reducing the NOx discharge from the fuel injector. Because they have found with the sac volume, the fuel injector which is delivering oil tends to cause more NOx formation in the combustion chamber and thereby discharge of the NOx to the atmosphere, which is a very, very polluting. So this is the second type of fuel injector that you're seeing. First one was the original one, and this is the second one. Now, I will show you the full injector as it is. Here is the full injector as it is. The lower part is what we described earlier, and this needle valve is lifted against a shoulder. That shoulder is part of the fuel injector body. Okay, and the shoulder of the needle valve and the shoulder of the housing is what distinguishes the needle lift or valve lift, how much the valve lifts. All right, this lift can be anything from 0.1 millimeter to 1 millimeter. You can imagine how small the lift is, and yet the quantity of fuel discharge can be a significant amount because the pressure is 200, 300, 320, 350 bar. All right. So this needle valve is kept under pressure by means of a spring carrier. This is the spring carrier on which a spring is loaded. You see, this is a spring which is under compression, and it is under compression by a distance piece. A distance piece is nothing but a cylindrical steel body which is collared to help hold the spring in position so that the spring does not shift from its position. And this distance piece is put under pressure by means of an adjusting screw. This is what you see is an adjusting screw with a slot on top. This slot helps you to fit a screwdriver in there and thereby screw the adjustable screw in clockwise or anti-clockwise because it is working against a threaded section. So more pressure you put on it, the more pressure will be on the spring, and therefore the needle valve will be seating much harder on the seat. So then you will require a higher hydraulic pressure to lift the valve, to force it against the spring and enable it to lift. Okay. Now, what is this leak off line? There's a fuel leak off line. You see, this needle valve and nozzle guide, what you see, is working in a very fine tolerance. That means there is no clearance really, but it can slide inside. It is made, machine made to finish. That means there is no scope of any oil leaking past this needle valve. But over a period of time, as it keeps sliding on the surface, what will happen? There will be some wear down. So, moment there is a wear down, that high pressure oil will find its way leaking past the needle valve into the space above the needle valve. So, when this path is full of oil, where is it going to go? So, this is a path which allows for leak off. And there is a connection here with a bit of a jack, with a nut and a pipe, a thin pipe. That pipe may be as thin as a pencil, as thin as a pencil. So that pipe proceeds and it goes little on the side of the cylinder cover, and there is a small funnel. You will have to notice once you go to college and you see the engine. There is a small funnel, and that pipe goes and places its position over there. So it is for the engineer to observe whether there is any leaking oil coming from there. If the leakage is in drops, if the leakage is in drops, it is considered satisfactory. There is nothing wrong with it. It is helping in lubricating the needle valve and the nozzle. Okay. Now, this helps to maintain the reduce the friction. But over a period of time, even if there is reduction in friction, there will be some wear and tear, and this clearance will gradually increase. So the rate at which the oil will escape into this passage will increase, and the leaking oil will again leak further. So from drop, 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 it will become drop, 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 and then there'll be a trickle. Moment there is a trickle means your needle valve and guide are finished. You have to change them. You cannot repair, you cannot overhaul. That is why the needle valve and the guide is considered as a consumable item for the engine. Just as cylinder liner, piston rings, gaskets, needle valve and guide, fuel pump, plunger and barrel, these are also consumable items. They cannot be repaired, so they have to be replaced. There's no questions about it. If you have any further questions on the injector, do not hesitate to put it down on the chat column. The moment I notice a question there, I will address it immediately. So this is the fuel injector as a whole that you've seen. And this is the fuel injector, which is a little more modern. And it has come about with the objective of reducing NOx and reducing trumpet formation. In other words, leaking oil which carbonizes at the tip is called trumpet formation. Now, these fuel injectors have improved over time. The most modern ones are used on the common rail system. This common rail system is the modern diesel engine, which is computer controlled. It is completely computer controlled. In other words, the exhaust valve operation that you saw, that as it is hydraulically controlled, but it is more or less electro-hydraulic controlled, because ultimately opening of the vent valve in the exhaust valve is decided by the computer operations. So your exhaust valve can be controlled for the time of opening, duration of opening, and end of opening. Likewise, the fuel injector also can be electrically or electronically controlled. So here you have an example of a fuel injector. This is one type of fuel injector where it is using a solenoid winding. In the much more advanced ones, what we use is a piezoelectric system for fuel injectors. You can write it down. Modern fuel injectors, they use piezoelectric. What are piezoelectric? They are basically quartz crystals. You might have seen cigarette lighters where you press and tack, it makes a sound. And that sound is actually allowing generation of a voltage to jump from one point to another in the form of a spark. And that spark ignites the gas inside the lighter. So these piezoelectric systems, they have wide applications in all engineering disciplines, whether it is marine engineering, mechanical engineering, electrical engineering, civil engineering. Piezoelectric systems have come to rule the roost. They have become very popular. So in your off time, you can go into details about piezoelectric devices. They are actually quartz crystals. Piezoelectric means quartz crystals. They may be tourmaline, germanium. So there are some products, lots of them are there, which when on the application, let us say a crystal, a quartz crystal, if it is put under pressure, then more pressure it develops a electromotive force, a potential voltage between the two surfaces. More the pressure, more the voltage. And this voltage is ultimately amplified. And this amplified factor is set to the computers for control. So that is in-depth subject. But right now here we have is a solenoid winding inside a fuel injector. Now this kind of fuel injector is used only in the common rail systems. What is a common rail system? Common rail system is the more modern diesel engine where you may not need a camshaft. There is no camshaft really because your exhaust valve is as it is being operated by means of signals coming from a computer. It does not need the rocker arm, push rod, cam, etc. Similarly, your fuel injector does not need a hydraulic pressure to open the fuel injector. For a common rail engine, you have a common pipe which is very, very strong. And this common pipe holds fuel oil at a pressure in the region of 2000 bar. Anything between 2000 and 3000 bar is the pressure inside that pipe. Now there is only one pump, one fuel pump, which is a positive displacement pump, which will keep pumping the fuel and keep pressurizing this particular pipeline. This highly pressured pipe is called a common rail. It is common because from this pipe, you have individual pipes going to the fuel injectors of every unit of the engine. And this pipe which is going to the fuel injector actually is connected to the top of the injector as you see here. In this case, there is a filter here also. A very fine filter must be. So this oil goes right down to the bottom and the pressure here is about 2000 to 3000 bar of fuel pressure. So that the fuel pressure is readily available at the tip of the fuel injector. The pump does not have to build pressure anymore. Pump has already built pressure and the pressure is retained in a common pipe, which is called a common rail. All right. Just a minute, there's a phone call. Ooh, spam. So now this fuel oil, which is under pressure at 2000 to 3000 bar, is also in this pipeline into the injector and right up to here. So right up to this tip is the pressure of fuel oil. All it needs is a signal for this spindle to lift. And that signal is electronic or electrical signal coming from the computer to a connection over here. And this connection gives supply to this solenoid here. So the signal coming to this solenoid will control the beginning of injection, the end of injection, duration of injection, and rate of injection. Remember, 4 different controls are enabled over here. Beginning of injection, that means start. And this start may be varied depending on the load of the engine. If the load is under part load condition, the injection will be little later. If the engine is on full load condition, then the injection is normally advanced a little bit. Considering that ignition delay. I think I explained to you what is ignition delay. So this is very essential that anytime the load on the engine is increased, you need to change the timing of injection. So this helps in getting better quality combustion and ultimately a much better thermal efficiency. Okay. So if you have any questions, do ask. In the sixth semester, we will do common rail systems in complete. Right now, you're giving and being given an idea of only the fuel injector and a very sketchy concept of what a common rail diesel engine is about. In fact, common rail diesel engine has becoming more and more common. All the vehicles that you see on the road, they are all having common rail diesel engine. The advantage of common rail system is it will not give you any smoke discharge. It is so well timed, the timing of injection, the duration of injection, all this ensures that there will be complete combustion and no smoke. No smoke. Sometimes these marine diesel engines, they are called smokeless engines because they are common rail injection. Their timing is so controlled that there will be never a situation where unburnt gases will be coming out from the engine. Okay, let's move on. And so this is the same injector. I've made a bigger diagram so that you can actually see it more clearly. The lower part, I have drawn it in a magnified version, so you can see the lower part a little more clearly. Otherwise, if I draw it in the same proportion of the injector, it will definitely be much smaller. So that's all. Remember, the sac volume is eliminated in the modern fuel injectors with the objective of reducing NOx and reducing chances of trumpet formation. Okay. So if you have any questions, you ask. So let's go over the rest of the PowerPoint program. Flashpoint, you have open flashpoint and closed flashpoint. Remember, so this flashpoint measurement is done by means of an apparatus called the Penske-Martin's apparatus. All right. So this is the minimum temperature at which a fuel gives vapors, which when on the application of a flame or spark combusts and goes off. I'm giving this to you in writing, and I'm still very sure people will make mistakes when it is asked in the examination. In the examination, they will say, define flashpoint. And I'm telling you, out of 10, 6 to 7 boys will make a mistake. They will still not be able to define. And I've been seeing this for years, year after year. In spite of hammering the definition into the boys, they still make the mistakes. So I hope your awareness that 6 to 7 boys out of 10 make the same mistake, even after reading, even after learning the definition of flashpoint, I hope you will not make the mistake. All right. Okay. This temperature is indicative. Okay. They will also ask you, what is the relevance of flashpoint? Why is it so important? Your statement is that it is important because it is indicative of how hazardous that fuel oil can be. You see, petrol is very, very hazardous. Diesel oil is a little less hazardous. Coal tar is almost no hazard. See, they have different flash points. Petrol has a flash point of minus 20 degrees centigrade. So it's definitely a hazard. Diesel oil has a flash point of anything at 43 to 60, 70, 80 degrees centigrades. So it is marginally a hazardous product, no doubt. All right. So now you have open flashpoint and closed flashpoint. Now I'm leaving it to you to find out what is the difference between open flashpoint and closed flashpoint. Okay. The next item is fire point. It is the minimum temperature at which a fuel gives vapors, which when on the application of a flame or spark combusts and continues to burn. See, in the first case, the flash point goes off after flushing. But in the second case, where the fire point is, it continues to burn. So obviously the temperature of the fire point, the level of temperature in the fire point will be higher than the level of the flash point because the gas given off from the fuel is a continuous, and in this case it is momentary. So this is the distinction between fire point and flash point. Next, what we have is the ignition point. It is a minimum temperature at which a fuel or vapor combusts without application of flame or spark, and it is relevant to compression ignition engines because it is because of the ignition point that the combustion engine works. You see, you may have LNG, you may have LPG, but they are useless in a compression ignition engine in spite of them being used as the fuel. Why? Because their ignition point is super high. Their ignition point is anything like 550 to 600 degrees centigrade. And that is not a temperature that can be achieved by compressing air. So that is why wherever you're burning LNG, you need to inject a little bit of diesel oil. So moment you inject a little bit of diesel oil and then you inject the LNG, and that compression will first ignite the diesel oil. And once the ignition of the diesel oil takes place, the fire or flame spreads to the gas also. So it is not a compression ignition engine is only limited to diesel oil, remember, not to LNG, not to LPG, and not to ammonia engines. Ammonia engines are also going to come into being, and they are going to be similarly used as LNG. Only problem is, again, they have a problem. Only problem is they again have a problem. And that problem is it is not able to ignite on auto ignition because the temperature, auto ignition temperature of ammonia is something like 700 degrees centigrade. And then again, you can't use it. So again, you have to inject diesel oil. So ammonia as a fuel also has a failing. Why? Because it requires diesel oil to be injected. And our program is to have a carbon-free environment by 2050. How can you have a carbon-free environment if you're going to use ammonia and then inject diesel oil to help that ammonia to burn? Because ultimately what you burn with the diesel oil, you're still going to discharge carbon dioxide. So once you discharge carbon dioxide, you're not going to get a zero carbon footprint. And our objective is to get a zero carbon footprint by 2050, which means all hydrocarbon fuels are going to go, whether it is LNG, LPG, or whatever. The only fuel that is capable of fulfilling this promise is anybody? Hydrogen. The only fuel that is capable
Hydrogen.
of, yes, the only fuel that is capable of fulfilling this promise is hydrogen. So I would encourage you boys to think on those lines. Now, hydrogen, it has got enormous energy density, which means for its mass, for unity mass, it has 3 times the fuel density as a fuel oil. So you need 1/3 of the space on the ship for the same amount of diesel oil. So it is definitely advantageous. The only thing what we are lacking is means of keeping that hydrogen on board without having any mishap. The means of drawing that hydrogen into the engine without any mishap. So it is not that hydrogen cannot be used. Hydrogen can be used. Only thing is handling means have to be researched and improved upon. That's all. If you want a zero carbon footprint, I don't see any other fuel coming into the picture. Not LNG, or the LNG cannot be at all because it's methane, that's carbon there. Ammonia was a good product for use unless they change the means by which the ignition can take place. Ignition of ammonia by compression ignition engines is not possible because it requires an ignition temperature of around 700 degrees, 650 to 700 degrees centigrade. And that is not achievable by compression of air. Compression of air, you get maximum 300 degrees centigrade, maximum. Your diesel oil ignition temperatures, anything between 220 to 250, 260, like that. So you don't need a temperature beyond 250 or 300 degrees centigrade, but you don't get that 650 degrees centigrade under any circumstance. That's not possible. So ignition point is the minimum temperature at which a fuel or vapor combusts without application of flame or spark. That is why it is relevant to compression ignition engines. cloud point. Now, this cloud point is another problem where you have distillate fuels. Distillate fuels, which are paraffinic in nature, there the wax in the fuel starts freezing out, especially when the temperature is very cold. Your tanks are liable to be filled up with wax, and you can't pump that oil. It's very good quality for burning, but the temperature is so cold that it is no longer oil, it is blocks. It becomes like blocks of wax. And inside the tanks, I have seen some pictures also. These are yellow colored wax. So cloud point is the temperature at which wax starts to crystallize out from the fuel. Initial stages, the fuel will become opaque. A transparent fuel will lose its transparency, and there will be a misty color, mist. And that mist, if it is allowed to continue, it will form wax. The moment it forms wax, you cannot pump it. It's not a fluid. You cannot transfer it from one tank to another. So then you need heating inside the tanks to keep the oil always warm. For marine fuels, this is applicable only to distillate fuels and in the DMX group only. You remember the chart I gave you for IS 8217 2017. There you have for the distillate fuel DMX, DMA, DMB, DMDE, and then DF is also included. So those are distillate fuels. And this cloud point is relevant to only the distillate fuels on the paraffinic group, which is DMX. Okay. Pour point. Pour point is the minimum temperature at which oil can flow or it can be poured. It can be poured, then you know that is the last temperature. It is found or determined for a particular fuel under a test condition. Under a test condition of ISO 3016. There is one more point I need to break this part of it. Okay, let's first finish this and I'll tell you. Very important it is. Carbon residue. What is carbon residue? This is also a very important characteristic of fuel oil. You see, some fuels, they burn very easily and there is no smoke. Some fuels burn with partial smoke coming out in spite of giving it normal air. And in some cases, you will get only smoke. It is something like car tires. Yeah, you must have seen car tires burning on the road. They burn, no doubt, but the amount of smoke they discharge is horrible. So that is a sort of a kind of a fuel which has enormous carbon forming tendencies. So carbon residue is a characteristic of the fuel, and it is the tendency or propensity. The more accurate word used is propensity, which is also meaning tendency, no doubt, but it is a little more expressive when you say propensity. It is the propensity of carbon deposit formation under high temperature conditions in an inert atmosphere. Okay, so a fuel is also gauged by how much carbon it forms when it is burnt. If it doesn't form any carbon, everything is being burnt out, it's a very good fuel. But if it is giving a lot of carbon discharge, then it's not a very good fuel for marine engines. So that is why you need to have a gauge or a measurement of how much carbon a particular fuel will give. So this is done by having three different means of gauging a fuel. And these three means are tests which give you a CCR. It is called the Conradson carbon residue. It can also, by another test method, you have another reading which is called the RCR or Ramsbotham carbon residue, and a third one which is called microcarbon residue. So these are the different measuring arrangements. It is something like saying centigrade, Fahrenheit, and Kelvin. Ultimately, they are all giving the same, the temperature. So Conradson carbon residue, Ramsbotham carbon residue, and microcarbon residue, one of them will be listed on the chart. And let us see which one it is listed. residual fuels. Okay, here you are. Let's go on to, yeah. You see on the third level, viscosity is first, density is at 15 degrees centigrade, and then microcarbon residue in 96, or what is that? Percentage by mass. In the best of oils, in the residual fuels, you get 2.5. That means this is one of the best oils that you can get, and the carbon residue is 2.5. In the next one is 4 times as much, RMB. And then in the RMD, it is a little more. And RME, it is still more. And in the worst one, you have almost 8 times more than the best ones. So never we use this oil on board the ship. I don't remember what was the level, but I think RMG is the last one that we have used. One of the worst ones is RMG, and then you have specifications RME, RMB, RMD, RME. R is residual fuel, and this is the microcarbon residue in percentage by mass. So that is how it is measured, and it has to be specified in your bunker delivery note. The supplier who gives the oil will also specify what is the MCR. Sometimes it is given CCR. So these are given. This parameter gives an indication of combustibility and deposit formation tendencies of the fuel. Remember, what is the purpose of having MCR or CCR? It gives a parameter which gives an indication of combustibility and deposit formation tendencies of the fuel. I can't put it in better words. Okay. So this is what it indicates. You may have a very good engine, you may have very good engineers, but ultimately you see smoke coming out of the funnel. So it is not the fault of the engine, it is not fault of the engineers. It is the fault of the fuel. So best is to choose fuels which have a low carbon content, carbon residue forming content. Next is ignition delay. What is ignition delay? This is the time period between the instant fuel is injected into the combustion chamber till the time it commences the combustion. This is also referred to as ignition lag. All right. So this ignition lag with ignition delay, same thing. That means if a fuel is not of quick burning, we put it in, it doesn't burn. And there are several reasons for it. It is not only quality of the fuel. There are other reasons for which you can have an ignition lag. If your atomization and penetration of the fuel is not satisfactory, there also you can have an ignition lag. Okay. Now here, look at this diagram and memorize this diagram for good for the rest of your life. You have to memorize this diagram full. Now we have a graph with a representation. Let's make it full scale. So far, no questions. Shubhankar, I see no questions, so I'm making it full scale so you can see this diagram a little better. And yeah, so now let's have a look at this diagram and study it. Now, this is the compression pressure, and it is the graph is pressure against the crank angle. So there will be a position where it is TDC and BDC, etc., and how many degrees before TDC, how many degrees after TDC, etc. So when the compression takes place over the crank angle, as the piston keeps going up, the pressure keeps rising. This part is called the compression curve. And during the curve, well before, not well, say about 12 to 14 degrees before TDC, you remember your timing of the fuel injection. 10 to 12 degrees before TDC, fuel is injected at the point A. All right. The compression is still continuing, but the combustion has not started. So as the compression continues, there will be a point at which on the compression line before TDC, then the commencement of combustion starts, or rather commencement happens. All right. So when the fuel combusts, obviously there will be heat release and pressure rise. This heat release simultaneously with pressure rise shows the pressure rising up on this graphical representation till the point of TDC, and even after TDC there is a slight pressure rise. So point C is the point of TDC, and after TDC also there is a pressure rise till the piston starts effectively coming down. So rate of pressure rise and rate at which the piston is coming down, the rate of rise is much more. So then the fuel is still coming in. Fuel has started injection at point A, it continues at B, it continues at C, and it continues till point D. All right. So it is, say, 14 degrees after TDC and 12 degrees before TDC. So the fuel continues up to point D. But by that time, the fuel is burning as well as coming into the combustion chamber, both. And the piston is also coming down. So that is why, because the piston is coming down, and in spite of fuel being added and burnt in the chamber, the pressure is shown to come down. This is the expansion line. This is the expansion of gases which is causing the force on top of the piston. And this piston is ultimately, thus force on the piston is ultimately what draws the torque or rotary force on the crankshaft. So this is the graphical representation of the expansion part of the gases. So remember this diagram, you have point A where fuel is injected. No combustion takes place. At point B, fuel starts to burn. That means combustion takes place. Moment it takes place, there is heat release and increase in pressure. So moment the pressure rises, it is shown by this graphical representation. It even crosses the point which is the top dead center on the crank, and the pressure keeps rising in spite of the piston coming down. That means the rate of combustion pressure rise is faster than the rate of expansion. So the pressure is shown as a slight rise. And then thereafter, in spite of fuel being injected and combustion taking place, because the piston chamber, or rather the combustion chamber volume increasing with the piston coming down, there is a drop in pressure. And this is the expansion of the gases. The period between A and B is called ignition delay. All right. Is this very clear? I hope it is very clear to everybody. So remember this diagram very well. If you're asked to explain what is ignition delay, you can put it up to them. Next. Oh, what is this? It's become very large, yeah? Okay. This delay period, it consists of two delays actually. One is the physical delay, where atomized vaporization and mixing of fuel, air and fuel takes place, and that rise in temperature and rise in temperature. See, the fuel, while it is inside, it starts atomizing. It has come out from the nozzle and it starts atomizing, breaking up into small parts. Then surface of it vaporizes. The small particles, they vaporize and they mix with the air. And the time taken for rise in temperature. So this is the physical delay. And there is a chemical delay also. And this chemical delay is largely the chemical reaction of oxidation. Oxidation is basically a chemical process. So this chemical process also takes some time. So the fuel reacts before it can start to burn. So the physical and chemical delays occur simultaneously. To reduce NOx, the method adopted in modern engines is to reduce the ignition delay. Now you see, I had told you before that if at all you have a situation where the ignition delay is very large, all right, very large meaning the fuel comes in, but it doesn't burn for quite some time. So this quite some time means more fuel is coming in. As the more fuel comes in, there is a large amount of fuel which is not burnt in the combustion chamber. But the initial part of the fuel which has come in will now start to burn. And once it starts burning, then the rate at which the flame travels is 2.5 kilometers per second. Yeah, kilometers per second. And this rate of rise in pressure is super high. And this results in knocking of the engine. I hope it is quite clear. Okay. So physically to reduce the ignition delay. Next is ignition quality. It is the ignition quality delay combustion characteristics. Sorry, it is the ignition delay combustion characteristics and tendency to knock. It mainly depends on the form of hydrocarbon compounds in the fuel. So if you have different chemical formulas, C2H2, one is C16H34. So different chemicals compound of the hydrocarbon will cause different delays. Next, what you have is a cetane number. Cetane number is a measure of ignition quality. It is indicating to you how good the quality or how good the fuel is. And this ignition quality measurement is given by a number. So a high cetane number indicates a short ignition delay, and a low cetane number will indicate a long ignition delay. That's the way it is. For low speed engines, the cetane number can be as low as 24. But for medium speed engines, four-stroke engines, they will require a cetane number of 35 and more. They indicate what is it. So what is cetane number? Cetane number is a number given to a fuel, and that cetane itself is not there in the fuel. Cetane by itself is a hydrocarbon which has got very good burning or combustible characteristics. You can say cetane has almost zero ignition delay if it was used as a fuel. All right, but it is given an index of 100. Similarly, the antithesis, which means alpha methyl naphthalene, that is also a hydrocarbon, but it has got very, very poor combustible characteristics. It has got very long ignition delay. So that is given a index of 0. Okay. So now a combination of cetane and alpha methyl naphthalene is a sample fuel which can be equated to an actual fuel which you are going to use. The actual fuel which you are going to use has a cetane number, but you don't know what is the cetane number. So if you need to find out, you need to burn this fuel on a designated engine and measure the power it is giving per unit mass of fuel burnt, what are the temperatures, and what are the other parameters. Then you need to have a combination of cetane and alpha methyl naphthalene, which when burnt in the same engine will give the same characteristics. All right. So this mixture of cetane and alpha methyl naphthalene, where cetane may be 30% and alpha methyl naphthalene 70%. So a combination of 30% cetane and 70% alpha methyl naphthalene gives you a fuel which burns with equal intensity and equal power and equal parameters as the sample fuel. Then that fuel can be said to have a cetane number of 30. I hope you are able to understand. So cetane number is only for DMA, DMB, and DMX, not DMA. I've repeated DMA. It should have been X. DMX, DMA, and DMB fuels, which means it is only relevant to distillate fuels, not relevant to residual or heavy oil, only distillate fuels. For heavy fuels, you have another measuring element, measuring scale, and that scale is called Calculated Carbon Aromaticity Index, CCAI, and in some cases, calculated ignition index. We don't go into much of calculated ignition index, but it is another parameter which can be used to measure the ignition quality of a fuel. The CCAI is intended to measure the ignition quality of a fuel, and this fuel is only residual fuels. All right. For residual fuel, the ignition quality can be expressed as CCAI or CII. It is calculated carbon aromaticity index or calculated ignition index. Lower the CCI, better is the ignition. The recommended limiting value is 870. So if you have a fuel with a CCAI of 870, it is the limit at which it can be burnt in your diesel engines. Anything above 870 is not permitted under IS 8217 for marine purposes. It will not come under marine fuels. All right. Now, what is the CCEI index? Okay. Your cetane number is a percentage of two different chemicals. And this cetane number cannot be found for your residual fuels. There are a lot of difficulties. I will explain that later. But CCAI is obtained through calculations, and it takes into consideration the boiling temperatures of the fuel. And ultimately, you have a long formula. This formula has been derived by Shell, the oil company Shell. There are two formulas actually. One has been designed by British Petroleum and one has been designed by Shell. It's a long drawn formula. I don't want to complicate our subject and go beyond the scope of our syllabus by giving you that. You will never be asked in your fifth semester regarding the formula. But I'm only giving it out in case you need to know where does this CCAI come from. This CCAI does not come from any experiments like your cetane number. It comes from a series of calculations. Based on those calculations, you have a formula wherein you can obtain the CCAI value of any residual fuel. Okay. Next, what we have is after burning. What is after burning? After burning, this occurs in the third phase of combustion. Now, we are going to do the different phases of combustion in the next PowerPoint program, and that will be in this class itself, because right now it is only 3 o'clock. We have got a lot of time. We've got more than half an hour. So afterburning occurs in the third phase of combustion. That means after the fuel has just been cut off. After the fuel has been cut off doesn't mean the combustion has stopped. The combustion will continue till the fuel is burnt, not when it is cut off. Okay, so this occurs in that third phase of combustion and extends over a longer period. It also depends on how good the fuel is. If the fuel is good, it will burn quickly. If it is not, it will continue burning even when the piston is near the bottom dead stroke. Okay, and extends over a longer period. This has several causes. What are those causes for afterburning? Actually, I have given you only 5, but you can have even 10 or maybe more also. So these common causes for afterburning is incorrect fuel grade. That means you've taken the wrong grade of fuel because it doesn't burn within that limited time. Number 2 is bad atomization. If you don't give proper atomization, let us say what is bad atomization. That means inadequate atomization. Just a minute, my thing is coming over. Sorry. The computer is showing low power. No change. No change. Okay, now we are in. Yeah. My battery is 27%. Okay. So bad atomization would mean either too much of atomization or too little of atomization. It can't be midway. Midway means correct atomization. I told you 20% should have small particles and 80% should have large particles. So if it doesn't have that, it will give you incomplete combustion. Incomplete combustion means the fuel will not have burnt by the time it reaches the end of the stroke. Next one is incorrect injection pressure or timing. If the injection pressure is incomplete, then the quality of atomization, penetration, that will be affected. If the timing of the fuel pump is not correct, that means it will be injecting far too late. Well before the piston has already moved down, then you inject fuel. Or if you inject well before, when the temperature has, when the pressure has not come up, then also the fuel will not burn. So these are reasons, some of the reasons. Second one is insufficient air supply. If you don't give it enough supply, the oil which is burning will burn partially, and the rest of it will go as unburned fuel, which is carbon. So there will be a discharge of carbon from the engine. So this continuity of burning, it can be a combination of all these. Sorry, I got my hearing, earphones on, and I put on the wrong switch. Anyway, so a slow burning, high viscosity. So these are the five basic reasons for afterburning. You can have more reasons for afterburning. It is not end all and be all of the list. It is not exhaustive in nature for afterburning. So slow burning, high viscosity, high carbon content fuels may also cause afterburning. Afterburning is a one word and it has to be hyphenated. Afterburning. Afterburning is a term which has to have a hyphen. Okay. So cause afterburning. Afterburning is a term. All right. So don't make a mistake. It is a combustion process continued even after the combustion stroke. I think that is reasonably clear to understand. What is afterburning? The last sentence says it all. It is the combustion process continued even after the combustion stroke. That is what is afterburning. All right. So that finishes our this particular plate. But don't run away. I have another plate for you. Okay. So we'll go and oops, let's save it. Okay. Okay. So that afterburning was our last topic that we started on. Now what we are going to go into the later part of it as the combustion process. This combustion process may be considered, actually it is three phases, but in some cases, let's let's keep it at three phases. Sometimes it is exaggerated in a diagram with four phases. Phase one, the tiny atomized fuel droplets delivered into the combustion chamber at the start of injection will evaporate and mix with the hot compressed air. Some chemical changes then occur. The mixture will reach an ignitable condition and spontaneous combustion will begin. That is the first phase. There will be diagrams which will give you a better explanation of where is the first phase. The second phase, let us see. The second phase is ignition as it starts. That means from the point of injection to the point of ignition delay or the commencement of ignition. That is the first phase. The second one is ignition and commencement of combustion will set up a flame front. That means the fire will start, which will accelerate through the chamber and spreading and burning all the other droplets present, whether they are medium-sized droplets, whether they are big-sized droplets. Once the flame starts, it will encompass all the droplets, burning all the other droplets, causing a rapid heat generation with corresponding rise in pressure and temperature. Right? So once the ignition starts, even the big drops which are there, the flame will start encompassing them, and then combustion will continue. So here is the diagram which shows you it not three but four phases they have given you. So the first stage is from the point of start of injection to the start of combustion. You see point one. That is the first phase of injection, first stage of combustion. All right. The second stage of combustion is actually given from the point where the combustion starts to the point of TDC. TDC is 0 degrees over here on the crank angle. So this is the second stage. I would like to increase this right up to what they have shown as 0.3. Right up to here it should have been. Okay. Then it would have made more sense. But he has made it up to TDC. I don't see why he has included to TDC. It should have gone right up to 0.3 where fuel injection is stopped. That should have been. fuel injection stopping over there does not mean combustion has stopped. Combustion will continue till the fuel is burnt. So from point 3 onwards, the fuel continues. And he has not given the state. What is the stage 4? Stage 4. Actually, this point 4 is the point at which the fuel injection stops. From it stops, but the combustion will continue and expansion of gases will continue. So this is the diagram which will tell you the injection period is over here. This whole duration from here right up to here. So at point between 3 and 4 up to this point is where fuel is injected. Okay, that is what it is. This is your atmospheric line and start of everything else is the same. Motoring, what does motoring mean? It is the compression pressure without the fuel injection. That's all. If there was no fuel injected, then the line would have followed this route, come on that and come out again. That is the compression line. The compression pressure rises up to this much, which is equal to whatever, 50. And then it goes down again. Your peak pressure is shown around 80. Okay, so this is your stages of combustion. You can make a simpler diagram if required and move on accordingly. So you saw the first phase and second phase. Next is the third phase. The third phase, following the rapid pressure rise in phase 2, hot turbulent conditions existing in the combustion chamber will ignite and burn the remainder of the measured fuel charge as it gets injected. So as the fuel keeps coming in, this flame will burn that oil. For that fuel, there is virtually no ignition delay. The ignition delay is only at the initial start of the combustion process. At the later stage, when the fuel is coming in, it burns instantaneously. So there is no ignition delay for the oncoming fuel. But ignition delay is at the start of fuel being injected. Remember that. Okay. This is the phase 3 and is the controlled part of the combustion process. As pressure is regulated by the rate at which the fuel continues to be delivered. All right. It is the controlled part of the combustion process, and the pressure is regulated by the rate at which the fuel continues to be delivered. If the fuel is delivered faster, then the pressure coming down will be much slower. That means pressure will remain high. So that is the third phase of combustion. Now, what is diesel knock? While ignition delay occurs, injection of fuel continues. That means the fuel keeps coming in when there is a delay. When a substantial quantity is delivered and the fuel ignites, a very rapid rate of rise in combustion and thereby pressure occurs. This rapid rise in combustion is termed as detonation. It's an explosion. The shock loading with noise on the engine from the noise from the engine is called diesel knock. I think I should put it in inverted commas. It has got nothing to do with the fuel, but it has got with the delay time period with diesel knock. All right. Now here is a diagram which I showed you before, and this was showing the ignition delay. The same diagram I have improved upon it to show what is diesel knock. You see, where the ignition delay is small, the pressure can rise up to a certain amount and then be allowed to expand. Where the ignition delay is large, the quantity of fuel coming in from this point to this point is definitely much more. And when that fuel ignites, most of the fuel will start igniting with a flame front of 2.5 kilometers per second. So then the pressure will rise so rapidly, it is like a hammer blow. This rate of rise of pressure, which is called the gradient, is so steep that it is almost like a sledgehammer being hammered on the top of the piston. So that is why ignition delay up to a certain amount is acceptable. If you have diesel knock, that knock is actually coming on the top of the cylinder, on the piston, And from the piston, it is coming to the crossed bearing. From the crossed bearing, it is coming to the connecting rod. From the connecting rod is going to the bottom end bearing and crankcase bearing. So all your bearings are going to get damaged. Your bearings are the weakest in the line of forces because these bearings are made of white metal. And white metal is a very soft metal. And the soft metal is backed up by steel. I showed you thin shell bearings, and this steel is okay. But what happens to the white metal layer? That gets damaged. Moment that gets damaged, your lubrication is affected, and the entire bearing will fail. It will fail. There's no choice. Okay, so that is that. So let's go on to the next thing. So I hope you understand this diagram well, because it was in the old diagram that I've superimposed the diesel knock. So I have not written anything extra, except that over here it is written as diesel knock. So this rate of rise in pressure is indicative of diesel knock. Okay, so we saw this one. This is a diagram I got from the net, which is showing how the fuel is dispersed once it comes out from the nozzle. See, when the fuel in that sac volume emerges through the nozzle hole, it is like a venturi. That venturi will cause cavitation. You understand what is cavitation? Samir, sir, please repeat the causes of diesel knock. Repeat the causes. Okay, let's go back. Yeah. While ignition delay occurs, that means ignition, that the fuel has been injected and it is occurring. The delay is occurring, which means fuel is going in, but it is not starting combustion. So injection of fuel continues. So when a substantial quantity is delivered and the fuel ignites, that means the early part of the fuel ignites. That which has already come in, it has atomized and it is raised to the ignition temperature, that will ignite. But the latter of the fuel will not ignite immediately. But since the early part of the fuel ignites, the flame does not require the late part of the fuel to go through ignition delay. The flame will cause the entire fuel to burn instantly, almost instantaneously. Because the entire mass of fuel which is delivered in the combustion chamber burns instantaneously, the rate of rise in pressure is phenomenal. Because of this rate of rise being phenomenal, it comes as a huge hammer blow. It is like a knock. So that is why it is called a diesel knock. With substantial quantities delivered and the fuel ignites, a very rapid rate of rise in combustion and thereby pressure occurs. And this, it is like detonation inside. It's an explosion. And this explosion results in gas expansion. This gas expansion being so sudden, it is like a hammer blow on top of the piston and also on the underside of the cylinder. But the cylinder is definitely much stronger than the piston crown. So this piston crown gets that hammer blow on top, and that hammer blow ultimately affects the whole piston down to the crossed bearing. Then the crossed bearing, 9-1, somebody's calling. Just a minute, please. Some looks important. Hello, Keval Chen? From Marine House. Okay, আমি আসছি, নিচে আসছি. হ্যাঁ, আমি আসছি. Boys, let's take a 5-minute break because somebody from MMD has come downstairs. 5-minute break. I'll be back again. It is only 15:19. Okay, guys, we are back in class 26. That's taken me about 6 minutes. So, diesel knock is a very damaging factor for any engine. Ultimately, the force is felt by the bearings. So, if you have damaged bearings, don't complain that the bearing is poor quality or the alignment is wrong. You are not having proper combustion in the engine, thereby giving rise to diesel knock and causing. What causes diesel knock? Sir, please repeat what causes diesel knock. A large ignition delay will cause a diesel knock. That's the bottom line. Okay. Okay. So this was the original diagram, and this was the, yeah, this is a large ignition delay. Originally, the ignition delay, as you can see, is a small ignition delay, and because of that, there is some rise in pressure, etc., whatever. It cannot be that there is zero ignition delay. There will always, even with the best quality fuel, there will be a slight ignition delay. And this is attributed to, even if the oil quality is very good, it will take some time for the fuel to atomize, to rise in temperature to the ignition point and then start burning. So this ignition delay may be very short, it may be medium, or it may be very long. If the ignition delay is very long, then you have a condition of diesel knocking. That means the quality of the fuel is giving rise to diesel knock. It does not burn so quickly after introduction. So I got this diagram from the internet. It is partially explaining what are the products that are coming out from combustion: NOx, particulate matter, unburned hydrocarbon, and combustion efficiency. Where does combustion efficiency come about? This doesn't fit in. But what happens in the nozzle is a very rapid flow of the fuel. It is 250 meters per second, the flow of the oil that comes out at a pressure of 280 bar. So there is some amount of cavitation. Cavitation is an occurrence where a fluid flowing from a high pressure zone to a low pressure zone, it gives rise to bubbles which are within the fuel, within the fluid, to expand. And as it expands, it comes to the low pressure zone and then collapses. The moment it collapses, there is an impact on the surface. This impact is what causes pitting of the surface. This pitting is ultimately, it looks like corrosion, but is actually physical damage to the surface, not chemical or electrochemical. It is physical damage to the surface, and ultimately the nozzle holes, what you see here, becomes larger and larger in their diameter. Moment they become larger and larger, then the atomization does not happen. Or if it happens, only a very small amount of atomization takes place. And instead of a spray coming out, you start getting a jet. So the jet gives rise to very poor combustion because there is inadequate proportions of addition of atomization and penetration. Okay, let's go on to the next part. Now we are coming into the fuel injection part. The fuel injection system is the most vital function for satisfactory combustion performance and output of the engine. That is why the heart of the engine is considered in the fuel injection system. If you don't deliver the fuel correctly in the combustion chamber, you will not have proper combustion. Then you will get a lot of smoke, a lot of incomplete combustion, you'll get carbon, etc., etc. So your fuel injection system has to be top-notch for good quality combustion. Okay, the system needs to perform the following functions. It is a lot is demanded from the fuel injection system. Number one, it has to supply an accurately measured quantity of fuel to each unit regardless of load. That means when the engine is on part load, then whatever fuel it is delivering to each unit should be in equal proportions. for all of them. Okay. Number two, deliver the fuel at the correct time at all load positions with quick or precise opening and closing of the fuel valve. All right. That means your cam setting with the fuel pump has to be so accurate that it has to be given exactly, say, 13 degrees before TDC. All right. So at half load, it has to be still 13 degrees. Full load, it still has to be 13 degrees. This is for your manual operating systems, not computer controlled systems. Okay. The third factor is inject the fuel at the correct fuel rate. That means it is not giving one blow of oil. It is giving a continuous supply of oil. Now we are considering in terms of microseconds. So microseconds, it is like a flow of oil coming from the injector over a duration. So that rate at which the fuel is coming has to be a correct fuel rate. Otherwise, what will happen? The entire lot will go in one shot. And that is what is happening. So that is why you have the common rail system with electronic fuel injectors. They are better controlled than the ordinary injector. In the ordinary injector, you will have ignition delay, you will have diesel knocking, but in the common rail systems, you will not have any of these problems. There is no injection delay or diesel knocking for that matter. These are almost eliminated. That is why you have a controlled fuel rate at which it is going in. And number four, atomize and distribute the fuel in the cylinder without impingement on the piston crown and liner valve. This is one of the most difficult parts of the fuel injector. Imagine the fuel injector has to deliver the fuel in such a way that part of it has to be small, part of it, particles have to be large, and at the same time, it has to come under a very high pressure. And even with this pressure, the fuel must not go and touch the piston crown or the cylinder liner valves. If it does, you're damaging the engine. That means the injection is not satisfactory. So remember these 4 points. What is required in the fuel injection system, or what are the demands that has to be met in the fuel injection system? All right. So these are the 4 points. Next, last part. We are coming towards the end of our program, where it says compression ratios and design of combustion chambers. Now we are coming into a place where the end of that particular theme is. Large engines, which are two-stroke large bore, have relatively low compression ratios, that is 12 to 14, when compared to medium speed engines, which have 16 or higher. So your larger bore or low speed engines, they will have a compression ratio of 12 to 14, and in the medium speed engine will have 16 or higher, and of course higher speed engines will have still higher. Higher compression ratios are designed into high speed engines. Higher the compression ratio, still higher will be the peak pressures. And you know, I had told you earlier also, if you have higher compression ratios, your thermal efficiency also improves and your peak pressures thereby also increase. But then you have limitations. You have limitations to having higher compression ratios for large bore engines because the strength of the engine comes into question. If you have a large area and a high peak pressure, then the total load is the peak pressure multiplied by the cross-sectional area. Your load is very high. But if you have a small area and you have a high pressure, then the load is still not very high. That's the concept why compression ratios are lower in the case of large bore engines and higher in the case of medium and higher speed engines. Reasons for low compression ratio in large bore engines is to limit the loading on the piston crown and combustion chamber large surface areas. You see, the cylinder cover is not being talked of. Cylinder cover is made super strong. It doesn't break so easily. So that is why the concern is mainly on the piston crown and the cylinder liner. You see, there is not much of a remark on the cylinder cover because cylinder cover is made super strong, very strong. It can be made as strong as you want. The reason for low, okay, because the high cyclic loading on such large surface area will result in early fatigue failure. Understandable. You see, the pressure on top of the piston will cause the diaphragm. It's like a diaphragm actually. The piston crown is part of a diaphragm. So this diaphragm, when the gas pressure acts, goes in a little bit, and then when the pressure goes, it goes back in again. Again, when it goes, a little bit of a pressure there, again it relaxes. Again the pressure. So over a period of time, if this continues, what is going to happen? It is going to crack, and you can't afford to make it very thick. You can have bore cooling and all. Those are improvements to avoid a fracture. But the piston crown is subject to some amount of bending continuously. So that is why this high cyclic loading on such large surface area results in early fatigue failure. Okay. Next is variation of compression pressure and peak pressures during operation. The compression pressure, why will it vary? Why will compression pressure vary? If you have compression in the engine, why should it vary? Okay, let's have a look at it. Oh God, we got still some lots of time, yeah? Okay, we should more or less finish it. Compression pressure. One is leaking piston rings. The piston rings may be broken, it may be worn out, it may lose their spring tension, or the gaps in the piston rings may be in line, all of them, or the liner may be oval and the ring is circular. So there is a possibility that there will be air leaking past the rings. So your compression pressure will be varying depending on how the piston is positioning itself. Other than this, you can have leaking exhaust valves, leaking inlet valves. Mountings are not seated correctly. That means on the cylinder cover, you have so many mountings. If they are not fitted well, then the compression pressure will not come up to the real level, or it will keep varying depending on how much leak is there. The indicator cock also may be leaking. So this will cause a variation in the compression pressure. The cylinder head gasket, where the cylinder cover is fitted, there is a gasket. If the gasket is leaking, then again compression pressure will not be normal. It will be varying. Okay. Then other than this, lack of lubricating oil sealing between the ring and the liner. Now, I had told you one story about my inability to start a lifeboat engine. That lifeboat engine, because it is left outside for a long period and then you go to start it, it will not start easily. If you compress, there's hardly any compression. The air leaks past the piston rings. So what we do is put a little bit of oil between the piston and the liner, and that oil spreads all around. So when the piston moves up, there is a sealing by the lubricating oil between the ring and the liner. This makes it very effective in ensuring that the integrity of the combustion space is perfect or near perfect. So if the integrity of the combustion chamber is perfect, you will get a very good compression. But if the lubricating oil is not there on the piston rings, then the air will leak past the piston rings. You see, you must not take it for granted that a cylinder liner is absolutely perfectly circular. Never. Similarly, when a ring is fitted and the ring is fitted in the liner, it makes absolute contact on the entire circumference. It never happens. So that is why you have multiple rings. The place at where the top ring is not making contact, there is a gap, but the second ring will close that gap. Similarly, the second ring will not have total 100% contact with the cylinder liner everywhere because the liner may not be a perfectly cylindrical at some places along the entire stroke. Similarly, the ring, it is not a circular piece when it is outside. Similarly, when you fit it in, you compress it and fit it in. So at some places the pressure will be less, some places the pressure will be more. So the contact between the liner and the ring may not be even right through. So all these reasons makes it impossible to get 100% integrity in the combustion chamber when the piston is compressing the air. Marginal leakage will take place. Marginal leakage will take place. And we as engineers try to make it as close as possible to perfection. Right? So that is why lubricating oil is necessary between the piston ring and the liner to fill up that little hairline gap between the ring and the liner. And believe me, it is an excellent sealing because the entire thin strip of oil for the entire height of the piston ring makes an enormous seal. It's an incredible sealing. It is not easy to push out that oil from there. So it gives a very good sealing. Okay. Other than this, you have choked air filters, which gives a less amount of air. If suddenly you have choked the air filter, then the quantity of air coming into the engine will be reduced, so the compression pressure will also be less. Okay. So these are the variation in compression pressures. Now let's look at the peak pressures. What causes peak pressure variation during operation? So first one is poor compression pressure will give reduced peak pressure. If the compression pressure is not adequate, the peak pressure is also not going to be adequate. That is understandable. Next is if the air supply to the engine is irregular, it will automatically have compression pressure less and peak pressure less. Third one is if the fuel injector malfunctions, if the fuel injector is not able to atomize the fuel properly at times, and sometimes it is able to, if there is an air lock inside the fuel injector, again the quantity of fuel will be irregular, so the peak pressure will again vary. So these are the reasons why the peak pressure may have some variation. In your exams, you may be asked a question like, what is the cause of compression pressure and peak pressure variation during operation or when the engine is running?
Sir, I'm sorry to interrupt, but sir, now it's our time to move for our next class, sir. It would be
Okay,
start
okay.
from. Yes, sir.
Oh, sorry, I'm sorry. I didn't look at the clock. All
Yes, sir.
right,
No
so
worries,
much
sir.
for now. Okay, okay.
Yes,
I'm
sir.
sorry. It's
And
gone
sir,
to.
one more thing, sir. One more thing.
Uh,
Can you send us the PPT, the current PPT and the previous PPT, sir, to our email, sir?
sorry, sorry.
So can you send us the PPT, the PowerPoint presentation with which you are teaching, sir, for the current topic and the previous topic, sir?
I have not yet finished the current topic. Previous topic I'll send. I've not
Okay,
yet
sir.
finished the current
Okay, sir.
topic. Okay. Okay.
Okay,
Bye
sir. Thank
bye.
you, sir.
Take care. Go in time for your next class. Otherwise, I will be in trouble.
Yes,
Oh,
sir. Will do, sir.
Excuse me, sir.
oh, yes, yes. Okay. Go ahead. What is it?
Sir, do you have any idea when our exams will take place
Oh my
in
God.
semester?
No, so moment I get the information, first thing I will do is inform Shubhankar and he will spread the news to everybody. I am also alert about it and I'm trying to finish the last part of my syllabus. That is why I asked you, have you done crankcase explosions, cabin fire, and air starting line explosion? These three are also very important. So
Yes, sir.
I don't know when the exams, but it will definitely be, I think, by beginning of February. They have not yet given us the chart or anything. What I can do is I will ask directly from HOD and let you know. Today I will give him
Sure,
a
sir.
call. Okay,
Yes, sir.
right
Okay,
now.
Thank
sir.
you, sir.
Thank you, sir.
Okay,
Have a
Thank
good
you,
day,
sir.
sir.
okay, bye bye.
Thank you, sir.
Okay, bye bye.
Thank you, sir.
Okay, welcome.